Hello everyone, welcome to organolysis. So welcome to another session of name reaction series. Now in this video I will be talking about the important name reaction that is called Reimer-Teimann reaction. Now this name reaction is very much important for MSc entrance or any MSc or BSc undergraduate level, right? So this reaction is very much important, and in this reaction is found in 1876. The two scientists, that is Reimer and Teimann, they discovered first that from phenol they can prepare salicylaldehyde. Now how they prepared this? Now let's see the mechanism and let's see the reagents, let's see the substrate. So first of all, they have started with the phenol and they are using the basic reagent, that is the CHCl3, that is the chloroform. Another is the sodium hydroxide, NaOH. If in presence of this, if you heat at 60 degree temperature, you are getting these two product. But these two product is in major and minor. So which one will be major? So this is your major. As you can see here, this is you are getting in your 4:1 ratio, right? So this is your major one and this is your minor one. Now that is why it is called the thermodynamically controlled product, that is your TCP, that is 2-hydroxybenzaldehyde, and it is called salicylaldehyde, right? So this is you called salicylaldehyde. Now this salicylaldehyde is your major amount, that is 4:1 ratio you will get this one as a major one. So in this is your minor one, that is 4-hydroxybenzaldehyde. Now see that the mechanism is very much important for this reaction, and the question frequently asks that which kind of intermediate is formed during this reaction. So that is why this mechanism is very much important for this reaction. See the mechanism, that when we are using this chloroform and NaOH, this mechanism this reaction goes via a dichlorocarbene intermediate. Now what is that? Let's see that if you have the chloroform right in this way, and if you are using this base, so this OH minus can take a proton from chloroform and it will be like this. So you are getting this Cl3 minus. This is your negative charge. Now when the Cl will leave from the system, so Cl itself has a good leaving group, so that is why Cl can leave from the system and you are getting this product, that is your, so this is your vacant p orbital. So this is now an electrophilic one. So this is called your dichlorocarbene. So this is your dichlorocarbene, CCl2 double dot. So this is your dichlorocarbene. Now this will directly attack with the phenol. Now when we are using phenol in the basic condition, so this OH is hydrogen attached with this phenol, so it takes this OH minus can take a proton from this, so you are getting this phenoxide ion. So this is called phenoxide ion. It is stabilized through this conjugate manner. Now this CCl2 will react with this phenoxide ion. How it will look, how it will react in this way. So this is react, this because this is just a kind of substitution electrophilic aromatic. So that is why I am written over here, that is ACAR pathway. So I think you all may aware that what is ACAR, that is ACAR or SNAR, that is substitution electrophilic aromatic or substitution nucleophilic aromatic. So if you haven't any idea, so I will be making a separate video for that, right? Now this is your first step. Now when it is using when it reacts with this dichlorocarbene, then you are getting this product. So this product, now this is this CCl2 is getting negatively charged. Now this negative charge can take a proton from here and it goes via in this way, so that you are getting this kind of intermediate. Now the next step is that it can go over here, these bonds can go here. Now this Cl can leave from the system. So that is why you are getting this intermediate, and after that this OH minus directly attack over here. This can go here and this can go here, just because of it try to get its aromaticity back. Now after that these bonds can go here, this Cl can leave from the system in this way, so that you can see you are getting the final product, that is your aldehyde. So this is just kind of aldehyde substitution in your phenol kind of derivative. Now after this hydrolysis you are getting this O minus is OH. Now why this product is so stable? Now this product is so much stable just because of there is a intramolecular hydrogen bonding and chelate ring. So that is why this is your major one, whereas if you have the para product like this has no such stability, this kind of intramolecular hydrogen bonding. So that is why this is your thermodynamically controlled as well as your major product. Now the most important thing is that why we are using NaOH. If we are using KOH, then what will be the problem? Now since the problem is basically when we are using KOH as a base, then the predominant product is the para one. Now why this is para one? It is think that it's probably due to the larger size of the potassium, so it doesn't make any 6-membered chelate, this kind of 6-membered chelate, right? So that is why we are using NaOH. So that is why it can chelate also, and as well as your ortho product is your major one. If we are using this KOH, then para product will be your major one, right? So see the next abnormal product for this reaction. Now what is the abnormal product? Now why I am saying it's abnormal product? See that when we are using this pyrrole and using this kind of reagent, that is chloroform and KOH, we are getting this product is in major one, but in the side product as well as we are getting this kind of product. Now this is your 1, 2, 3, that is your 3-chloropyridine. Now how we are getting this product? See first the mechanism for it. Now when we are using this CHCl3 and KOH, so it will form the dichlorocarbene. So I am taking as a major one, that is your dichlorocarbene, and we are using the as a basic condition. So this nitrogen attached with the hydrogen, it takes a proton in the basic condition. So you are getting this N minus and K plus in the medium. Now it can react in this way. So just because this is an electrophilic addition and it can form a 3-membered ring. Now when we are using this as a negative charge, this negative charge can go here and this Cl can leave from the system, and that is how we can get this abnormal product as a side product from this Reimer-Teimann reaction. Now one of the important the abnormal product for this reaction is that when we have the para substitution. Now if what is mean by the para substitution, now you can see here that is your paramethyl phenol, that is your fourth position. This is your 1, 2, 3 and this is your 4, that is a 4 substituted product. When you are using this Reimer-Teimann in this compound, then we are getting this product as a major and as well as a side product, this one. This is your abnormal product. Now how we are getting this product? Now see first that in the basic condition, this O minus OH takes a proton, that is we are getting this O minus over here, and when we are using the dichlorocarbene, so it can go here, it can go here, and it can be attacked like this. So you can easily generate this ortho product, but that is why I am not writing the overall mechanism for the ortho product. I am just saying that how the abnormal product takes place. So that is how we can get this one. So this is your negatively charged. Now when you are using H2O plus, it takes a proton, and you are getting this final product, this one. Now one more question may arise, that why it is not hydrolyzed. Now if it is because of that it is a neutral compound, so that is why it is not hydrolyzed. And one more thing you can also predict, that it's a kind of neopentyl thing, neopentyl type of ring, so that is why it is sterically hindered, as well as so that is why the substitution reaction cannot take place in this type of compound. So that is why it is not hydrolyzed, and it is look like in this way, and it will not further hydrolyzed. So that is why this is your abnormal product. Now one of the important example for this reaction is that when we are using this CH3L3 NaOH in this kind of product, this kind of substrate, so what will be the product? So you can see here, that is you can easily predict the ortho will be your major product, but I am not writing the ortho product here, but I am showing you here that is the abnormal type of product and what is the consequence of this reaction. Now when we are using this chloroform sodium hydroxide, you can see here that is your para is substituted with this kind of ring, so it will generate CCl2 carbene, and this negative charge go here can go here and it will go takes this CCl2, it will attack with this CCl2 carbene, and it will form further, that is this kind of product. After this product formation, then if we are using this H2 palladium barium sulfate in KOH and ethanol medium, then these two double bond first hydrogenated, just because it is your hydrogenating agent, so that is why it will first hydrogenate, and this CHCl2 also after the hydrogenolysis you are getting this CH3 over here. Now when you are using this CrO3 acetic acid, that is your oxidizing agent, so if you haven't any idea of this oxidizing agent, you can go over here. I already make different types of oxidizing agents and oxidation reaction series. You can go over here for the overall reactions of the oxidation reaction, right? So this is if we are using this CrO3 and acetic acid, so that is why I am not writing the overall mechanism for this reaction. I already make that video. So this is your CrO3 and acetic acid. So this secondary alcohol is oxidized to this ketone, right? So this is your product from the abnormal product. Now let's see some different examples for this reaction. Is that if we are using this CCl4NaOH, then what will be the product? Now from the Reimer-Teimann reaction, we are using this CHCl3 and NaOH. Now if we are using this CCl4 in NaOH, then what will be the product? Now you can see here, that is in the basic condition, it will take a proton from here, so you are getting this O-, and after that these bonds can go here, it can attack here, and this Cl can leave from the system. And further that you will see that this CCl3 can easily hydrolyzed in the basic condition, so you are getting this product, this COH3-, and after this hydrolysis, after this removal of water, 1 mole of removal of water, you are getting this acid. And how you can get, you can see here, this is your COH. So it can leave in this way. So this you can see here, that is your 1 mole of water is leave from the system, so that you are getting this product. And after the final hydrolysis, you are getting this final product, that is your salicylic acid. So when you are using this CCl4, you are not getting salicylaldehyde, you are getting salicylic acid, right? Let's see some examples for this Reimer-Teimann reaction, which are important for your exams, right? Now when we are using this compound and if we are using this reagent, then what will be the product? You can see here, that is ortho is substituted, and this if we are placing this aldehyde group in this position, this ortho position, then the ring is, there is a severe steric repulsion takes place, right? So that is why the para product takes place, and this is how. And you can see here we are using this KOH, not NaOH, so that is one of the important case, that is why we are getting this para product in the major one. So this is your vanillin, so it's a kind of very much flavoring agent. This basically used for the making vanilla, right? So one more example is that if this is your catechol, now when we are using this catechol in this condition, then this is your major product, that is para to this OH, that is you are using same condition, that is KOH, so that is why you are getting this product. And if we are using this CH2I2 and NaOH, then this kind of product is being takes place. Now how this product takes place? See that you are using NaOH, so these two are formed, this O-, these two OH are from this O-, and we are using this CH2I2, so it will attack over here, 1 mole hydrogen will leave from the system. Similarly it will attack over here, and this hydrogen will leave from the system. So that is how you can get this CH2 insertion in this kind of product. So this is called piperenol. Now the next important reaction is that when we are using this indole derivative and with this reagent, then this is your major one, and along with this you will also get, this is your abnormal product. Now how will you predict the abnormal product? I already show you that when you are using this pyrrole derivative, you are using this CHCl3 and KOH, then this kind of product is being takes place. So the similar mechanism is also followed for this reaction. Now see the one of the important example, you can see here, this is your this kind of substrate. When you are using this CHCl3 KOH, so then this will be your major one. Now another important thing is that when you are using this substrate and H nu, and you can see here we are not using any base, we are using instead of base we are using this H nu condition. So this is called photo Reimer-Teimann. This is your photo Reimer-Teimann, right? So if you are using this, then it will follow the radical mechanism. So first it will this CH, Cl, Cl and one more Cl is this, so it will break in this way, and this OH will break in this way, they form the radical, and this O minus O radical and this CH radical will combine with each other to getting this product. Now one of the important and the last example for this Reimer-Teimann reaction is that we are using this condition and we are using this substrate and this condition, the same condition we are using that Reimer-Teimann, so you are getting this aldehyde in this position. So this is your overall examples for the Reimer-Teimann reaction. Now I hope I covered all those topics related to this NEM reaction, that is your Reimer-Teimann reaction, and I hope this video is very much helpful for you, and keep sharing my videos with your friend circle. And that's it for this video, and thank you so much for watching.